Welcome to this presentation on the Clang Compiler. Before we get to the Clang Compiler, you'd like to know the definition of a compiler. The name compiler is primarily used for programs that translate source code from a high-level programming language to a lower-level language, example assembly language, object code, or machine code, to create an executable program. A compiler is likely to perform many or all of the following operations, such as pre-processing, lexical analysis, parsing, semantic analysis, conversion of input programs to an intermediate representation, code optimization, and code generation. Compilers implement these operations in phases that promote efficient design and correct transformation of source input to target output. However, there are many different types of compilers. If the compiled program can run on a computer whose CPU or operating system is different from the one on which the compiler runs, the compiler is called a cross-compiler. A bootstrap compiler is written in the language that it intends to compile. A program that translates from a low-level language to a higher-level language is called the compiler. A program that translates between high-level languages is usually called a source-to-source compiler or a transcompiler. A language rewriter is usually a program that translates a form of expressions without a change of language. Now coming to the topic of discussion, the Clang compiler. Clang is a compiler frontend for the C, C++, Objective-C, and Objective-C++ languages. It uses the LLVM compiler infrastructure as the backend. It was publicly made available in September 2007 and its original author was Chris Lartner. It was designed as an alternative to the GNU compiler collection, also known as the GCC, which supports most of its compilation languages and unofficial language extensions. Its contributors include Apple, Google, Microsoft, ARM, and others. It is an open source software with its source code released under the NCSA license. Now coming to the languages supported, one limitation of Clang is that it supports only 4 languages, that is C, C++, Objective-C, and Objective-C++, unlike its alternative GCC, which also supports languages such as Java, Fortran, ADA, etc. Now, this picture represents a schematic view of the Clang architecture. The most important difference of its design is that Clang is based on LLVM. The idea behind LLVM is to use LLVM intermediate representation (IR). LLVM IR is designed to host mid-level analysis and transformations that you find in the optimizer section of a compiler. The rest of the architecture consists of elements that any basic compiler would have, such as the parser, the linker, intermediate code generator, and others. Now, like many other compilers' design, Clang compiler has 3 phases. The first phase is the front end that parses source code, checks it for errors, and builds a language-specific abstract syntax tree to represent the input code. The second phase is the optimizer, whose goal is to do some optimization on the abstract syntax tree generated by the front end. The third and the last phase is the backend, which the Clang compiler uses the LLVM compiler backend, which generates the final code to be executed by the machine, which depends on the target. Now coming to the strengths and the limitation of the Clang compiler. Due to Clang being a relatively new compiler, it has quite a few advantages over its relatively old counterparts. Clang is much faster and uses way lesser space compared to GCC, while supporting the same languages and providing similar functionalities. It provides very clear and precise diagnostics, which are error messages, and includes support for expressive diagnostics. Clang is very easily understandable for people familiar with the language being used. Clang inherits quite a lot of useful features from its backend LLVM, such as pluggable optimizers, ability to link in multiple code generators, just-in-time completion, etc. Having all these advantages doesn't deprive Clang of its disadvantages. Some of the disadvantages are that Clang doesn't support as many languages as its supposed alternative GCC. GCC also supports way more targets, and the front end of Clang isn't as mature as a GCC's, and the support of C++ isn't close to that of a GCC. It also isn't as popular or adapted as the GCC. The target hardware for Clang was originally the ARM version 7 and ARC64. Now we will talk about a few other compilers designed for specific functions. The Open64 compiler was specifically designed to work on parallel computing. The Intel Graphics compiler supports all major graphics and computes APIs, and its OpenCL compute stack includes compute runtime, compiler frontend and backend, and architecture specification of this Intel Graphics compiler is completely open source. The Small Devices C compiler. The SDCC is a free, partially retargetable C compiler for 8-bit compiler microcontrollers. The GNU Compiler Collection, or the GCC, is used to deal with embedded systems. This was a presentation by Kaushik Swaminathan, Venkatesh Jaya, Abhishri Jain, and Nevit Sister. Thank you for watching this video.